Hello guys, today let us see about the two concepts. First one is X-bit microcontroller or an processor. If we call that it is an X-bit microcontroller or an processor, what actually it means? That is my first talking. And next talking is critical thinking made by the ARM people to stand first in the industry. So this is the second thing I need to speak about in this video. First of all, the X-bit microcontroller or an processor. So consider an example called as an 16-bit microcontroller or an processor. So it can be an microcontroller or it can be an microprocessor. If it is called as an 16 bits, so that many bits of data is processed at a time in an processing unit. Here processing unit means an core of your microcontroller or an microprocessor. So 16 bit of data. So 16 bit of data are going to be processed at a time in your processing unit. So this is called as an technical meaning of X-bit microcontroller or an processor. So if it is an 32-bit microcontroller or an processor, it is capable of processing 32 bit of an data at a time. You can mark my words here, at a time. So 32 bit of data are going to be processed at a time in your processing unit. So if it is 32 bit, it is going to process 32 bit of data at a time in your processing unit. So processing unit is your core of your microcontroller or a microprocessor. Usually it is arithmetic and logical processing unit. So this was the answer for this X-bit microcontroller or a processor. If it is X-bit microcontroller and processor, that many X bits of data is processed at a time. So at a time in a processing unit. So this is going to make an effective mark over here, at a time. So many bits of data. So this X bits of data, if it is 16 bits, 16 bits of data is processed at a time in a processing unit. So this is the first thinking I need to speak with. So X-bit microcontroller and processor. So next one is critical thinking made by an ARM people to stand first in an industry. So this was the one of the major 4 or 5 points where the ARM people have been made changes in their architecture during the year of 1996 in order to come up with an more powerful microcontrollers. So this ARM people are going to design only an architecture. So this mainly the processing unit. The processing unit is going to consist of core, ALU and some of the external peripherals, attachable protocols they are going to be get designed with. So the overall microcontroller they are not going to design. They are going to design only the core part. See here. So this is my core part. So this is the LPC 1768 simplified block diagram. So this is the core part. So this is the core part which they are going to be designed by an ARM people. So rest of these peripherals. So this rest of the peripherals will be actually prepared by some of the external manufacturers. So it can be an NXPs or it can be any sorts of an silicon workers or silicon providers. They are going to get the core working. So this is your core working of your ARM. So this is going to be designed by the ARM people. So rest of the assembling, it can be an peripherals designing or it can be an DAC or it can be an external interrupts, PWM. So these are all going to be get designed from your external silicon providers. One of the example is your NXP. So they are going to have n number of silicon providers they are going to get deal with. So first critical thinking made by the ARM people during the year of 1966 is, so you are knowing that in an 8051 you are going to be dependent on an accumulator. You can just remember the commands of your 8051. So accumulator is the must in order to perform any of the operations. So these are some of the examples have been quoted here. So you have taken some of an resistor. In order to move to another resistor, you need an accumulator here. In order to move an immediate data, you need to have an accumulator. In order to perform addition, again you need to have an accumulator. So the dependency of an accumulator, so the accumulator is an intermediate. So this is your data and this is your processing unit. So accumulator is the only one medium which can take care of an data to speak with your processing unit or an core. So whenever the accumulator is busy with an one instruction, so next of the instruction or a rest of the instruction should be in an wait state. So this was the major disadvantages which have been conducted in an 8051. So because of this intermediate only one accumulator which is going to talk with an data and an processing unit. So this was the major disadvantages in order to make all the instruction to be in a wait queue. So all the instructions will be end up with an waiting queue till this accumulator is going to be get freed. So this was one of the disadvantages. So this ARM people, they have been seen these kinds of disadvantages. So sorry, this is an ARM. So that was one of the example LPC 176 set. So in every ARM, you will be having some sets of resistors. So all these resistors can talk with your processing unit. So instead of depending on only one accumulator resistor, here you are having a bunch of resistor. It can talk with an or it can make a communication between an data and an processing unit. So you can just see the differences of number of an resistor. So you can enhance the speed of the execution. So first and primary thing is speed of your execution is going to be get enhanced because the dependencies have been removed. Dependency of only one accumulator resistors have been removed and you are having a 15 set of resistors. So this 15 set of resistor can speak with your core of an processing unit. So this was the very much accurate thinking or an critical thinking which have been made during the time of 1966. See, these are the examples here. So R1 can speak with your core processing unit, R5 can speak with your core processing unit. So there is no wastage of an time. So there is no end upping of an waiting issues which have been happen in an 8051. So this was the very first critical thinking made by the ARM people, removing the dependency of an only one resistor, that is accumulator, to speak with your core. So this was the very much first critical thinking. And next one is thumb mode. So next one is thumb mode. So we are knowing that this ARM is an, so this ARM is 32-bit microcontroller. So second point is an thumb mode. So we are knowing that ARM is an 32-bit microcontroller. Oh, sorry. So that is having some issues here. Okay. So ARM is an 32-bit microcontroller. So it is saying that it is capable of performing an 32-bit data operations. So during the time of an 1996, so the 8051 PIC, they are going to rule the embedded systems field. So during that time, so all this microcontroller are going to be work with an 16-bit of an commands. So whereas your ARM is an 32-bit wider, if you are going to execute an 16-bit of an instruction, the rest 16-bit of an data or an power of your ARM is going to be get wasted. In order to address this issue, they are come up with an thumb mode. So it is going to work with an 16-bit of mode. So initially 32-bit ARM it was. So if you are having an 16-bit of an instruction, so first 0 to 15, it is going to hold that respective space or in respective processing area. So rest 16 to 31 bits are wasted. So you are utilizing only an 50% power of an ARM. So this was the condition which is going to happen during the time of 1966, because other 8051 PIC or any of the other microcontroller are capable of executing an 16-bit of an instruction. So if the same 16-bit of an instruction are going to be get executed in an ARM, so whereas this ARM is 32-bit wider, so first 15 bits is going to be get consumed by that instruction. So rest 15 is going to be get wasted. So you can just make an assumption here, only the 16-bit of data, mean to say 50% of power is going to be get utilized. So in order to address this issue, the ARM people have been came up with an thumb mode. If you are having any of an 16-bit of an data, the ARM is going to be switched from 32-bit to an 16-bit of execution mode. So here, so 0 to 15 is going to hold the first instruction. So next 16 to 31, sorry, you are having a spelling mistake here. First instruction or an command. So next 16 to 31 bits are going to get the fetch the next instruction. So first 0 to 15, if it is in thumb mode, 0 to 15 is going to fetch the first instruction. So next 16 to 32 bit is going to fetch the next instruction which is present in the code. So instead of executing a single 16-bit instruction, for a single execution, it is going to execute two 16-bit instruction. You can make a time execution here. So before it was executing only 16-bit. So now the ARM is being divided the 32-bit instruction into two 16-bit wider instruction. So first one is going to hold the first instruction. So second one is going to hold the next instruction. So due to this, so the execution speed is going to be enhanced. So it is going to execute two instruction for one line. So two instruction for one line. So this is called as an thumb mode. So this is another critical thinking made by an ARM people in a year of 1996, way behind 1996. So this was an thumb mode. So thumb mode is having its own advantages and disadvantages. In the later videos we can discuss about the advantages and the disadvantages of this thumb. So next one is, the next critical thinking made by the ARM people is bus speed variation. So this is another important critical thinking made by the ARM people. So this core is going to run at an 100 gigahertz speed. So this core is going to run at an 100 gigahertz speed, but whereas your DAC USB will be running at a lower speed. So the practical analogy is like, consider the bus, the city bus, not this actual bus. The city bus is running at an 40 km per hour. If the person who is walking at an 10 km per hour need to catch this city bus, he need to match the speed from 10 km per hour to 40 km per hour. If the speed is not matched, the person who is walking at the road may fall in order to catch this bus. If he is able to catch this bus, he need to match this 40 km per hour. If he is unable to match the speed of the bus, the city bus, and this walking speed, he is going to fall onto the road. So this is the another critical thinking. So this core is going to be run at an 100 gigahertz. Mark my words, 100 gigahertz. USB will be running at an smaller megahertz frequencies or something like that. So the mismatch of speed between an peripherals and an core, in order to achieve that, you are having an AHB buses. So you are having some of an AHB bridge. So this architecture is called as an AMBA architecture. AMBA. A stands for advanced, M stands for microcontroller, B stands for bus, AMBA. A stands for architecture. So this was another critical thinking, advanced microcontroller bus architecture. So it says that the core is going to be running at an 100 gigahertz. Consider your peripherals will be running at an slower speed. So this mismatch is going to be get addressed by this respective bridge. So you are having some of an bridge in order to make an mismatch of this speed. So 100 gigahertz speed and an USB speed. So one bridge or an handshaking protocol or an bridge is going to make an managing speed between this core and an peripherals. So this is another critical thinking which have been made by the ARM people in order to make an match between the speed of an core which is running at 100 gigahertz and an peripherals which is running at an lower speed. It can be an lower speed with an megahertz or an kilobytes, etc., etc. So this mismatch are going to be get managed by this respective bridges. So this is another critical thinking made by the ARM people during the year 1996. So next one is interrupt controller. So ARM is going to have an NVIC. It stands for, so here you will be having an NVICs. So it stands for nested vector interrupt controller. N stands for nested, vector, V stands for vector, I stands for interrupt, and C stands for controller. So nested means you can just assume here it is same as your nested if else. So one interrupt is going to be get serviced. So whenever another interrupt have been occurred during serving the first interrupt, so this is going to be get preempted if the second interrupt is having an higher priority. So like this, you can have an 240 nested vector interrupt controller. It can handle up to 240 nested vectors. So one below the other, it can handle up to 240 nested vector interrupt controller. 240 interrupts are going to be get handled by this ARM or an LPC 1768, and it is having an external interrupt which is going to be get supported by 4, and these numbers are dependent on an silicon providers. It can be an 240 or it can be an any number of an interrupts, or it can be an less than 240, 40 or 80. Based on the applications, you can customize all the architecture, because ARM is going to provide only the core. So the core is this one, only the ARM Cortex. So it is going to provide only the processing unit. So rest is dependent on an silicon providers. They can decide the number of UART they can provide, how many UART they are going to be provided. It can be 1, 2, 4 or etc. So it is going to be decided by the silicon providers. So these ARM people are going to provide only the processing unit. So rests are going to be decided by the silicon providers, and based on those applications, they can decide how many UARTs, how many CAN buses, how many DAC, or how many on-chip SPI peripherals, etc., etc. You can see all these things in an later videos, how this respective things are going to be get decided. So for this video, we are going to have another critical thinking, that is interrupt controller. The two nested vector interrupt controller. It can have an nesting of up to 240, and it can handle up to of an external interrupts of 4, and you can extend this respective numbers based on our application. So last and final critical thinking made by the ARM people is wake up and sleep interrupt. So one of the example here is, so if our mobile is in an off mode, it is called as an sleep mode. So whenever we are pressing this key button, so an switch on or an key unlock button, within a fraction of seconds, everything is going to be get activated. So everything are going to be get activated or going to be get wake up within a fraction of second. You can just imagine here. So by pressing a small button here, key press, so everything is going to be get wake up. So during an off state, So it is going to consume a very little much of energy. So it is going to reduce the power, or it is going to reduce the speed of the execution of an processor from 100 gigahertz to 30 gigahertz or something like that. So this is also another advantage which have been provided at an cortex or an architecture level customization. We can control the execution speed. If it is in an on mode, we are going to run the processing speed at an 100 gigahertz. If it is in an off mode, so this is in an off mode, so the whole processing speed is going to be considerably reduced. If we are going to reduce the processing speed, the power consumption is also going to be get reduced. So whenever we are dealing with an portable devices, power is a very major thing. So this ARM is going to handle this wake up and sleep interrupt, and that too in a fraction of seconds. You can just see here. So this is an sleep one. If it is going to be get pressed within a fraction of seconds, every devices or every peripherals are going to be get activated. So these are all the critical thinkings which have been made by an ARM people. First one is your dependencies have been removed. Only one resistor is going to be get communicated with an core one, that is going to be get removed. And next one is thumb mode. So it is going to execute 2 instruction if it is in an thumb mode. If you are having a 16-bit instruction, 32-bit ARM mode is going to be get converted into thumb mode, and an instructions are going to be get divided. So next one is bus speed handshaking. So core is going to run at an 100 gigahertz. USB peripherals are going to run at an lesser speed. So this is one they are going to make a critical bridging thing. So that is called as an APH bridge, or an simply an bridge, which is going to make an match between the speed variation between a core and your peripherals. And next one is nested vector. You are having 250 nested vectors. And last one is wake up and sleep interrupt. So wake up, so this is wake up and this is sleep. And last final thing is, so the power considerations are going to be get minimized if it is in a sleep mode. So please do subscribe for the channel, and please hit the bell button in order to have a notification. Please like, share, subscribe for this channel for an interesting topics on an LPC 1768. Thank you.